Hi everyone, welcome to my living room. I'm going to be giving my presentation today on flow batteries. I'll start with the basics. The very first battery is called the Baghdad battery. It was discovered in the 1900s, but it was invented over 2,000 years ago. But the battery technology has barely changed since. It has the same exact electrolytes and anode and cathode, almost identical to what we use today. Just some different chemistries, and we've definitely optimized a little bit. Basics of a circuit is that the electrons will flow from the negative side of a battery through the circuit, through the load, and then around to the positive side of the battery. Rechargeable batteries can reverse the process by, instead of expending energy out, it will input energy in and recharge the battery. The very first flow battery was invented by French scientist Charles Renard to power his all-electric airship. He got back only 5 times out of the 7 times he went out, so the technology was shelved, almost forgotten. It was revived by NASA in the 1970s as a potential storage for moon bases and Mars bases due to its reliability and durability. And then more recently, research universities and startups have been pushing new technologies and new chemistries such as all vanadium batteries, organic batteries, etc. We'll get into that a little bit later. Overview. Flow batteries are very similar to any battery that you can think of, except instead of the electrodes being made of the reacting material, the electrodes are neutral, and then the electrolytes actually get pumped around as a liquid, and that's where the reaction happens. They store the 2 electrolytes in 2 tanks, and they pump them together to the fuel cell in the middle, and then as the process goes, the 2 chemicals kind of equalize. And the main chemistry phenomenon behind it is called a redox, or reduction oxidation reaction, and we'll get to that in a little bit. Here's just a basic schematic of what a flow battery looks like. It really is just 2 tanks with separate electrolytes stored in. They get pumped around and meet in the middle. And then, as we were talking about earlier, the circuit having to be complete, from the negative side here, the electrons, due to the voltage difference, the electrons will get pushed around the circuit through the load and then around to the positive side. And the circuit is completed by having a membrane here that allows positive ions to cross, thus equalizing and completing the circuit. And this is an example of a lab flow battery. It looks exactly like that schematic. It literally is just 2 tanks, they get pumped, meet in the middle, and that's where the electricity comes from. Here's a blow-up of the fuel cell itself, the cell that is here in the middle. Very complicated, but essentially what happens is that the material gets pumped through here, and the membrane is where the magic happens. And then the good thing about these, just like regular batteries, is you can line them up in series to increase your voltage, your power, etc. Here's some examples of some industry flow batteries. It's still very new. There's only a couple of commercial applications so far, but again, it's the same thing. The tanks stored, and then the fuel cells here. The good thing is they're modular, so you can just add more of these depending on how much power you need. Again, here we can see the tanks again, and the cells are in here. Same process every time, very simple. So the basis of all this is the reduction-oxidation reaction. Essentially what happens is that one side, the oxidized side, will donate an electron, and when it loses that electron, it's said to be oxidized. The material that gains the electron, which is the positive side, will gain that electron, and it's called reduced because its total charge is reduced by adding that electron. The best way to remember it is the acronym oil rig. Oxidized is lose, it loses the electron. Reduction is gain. The reduced item gains the electron. It's a little backwards, but it makes sense. For example, when you're trying to solve one of these redox equations, we usually split it up into 2 half reactions that allow us to more easily analyze where these electrons are going and who gets what. So if we look at this first reaction, we can see that it seems balanced. We have the same number of aluminum on both sides, we have the same number of copper atoms on both sides. But the problem is that the reactant side only has a charge of +2, and the product side has a charge of +3. So not only do we need to balance the number of atoms, we need to balance the charge as well. And so when we split it into the reduction half reaction, the reduction is gain, so the one gaining electrons. We have our copper had a charge of +2 in the product, when the reactant had a charge of 0, so it must have gained 2 electrons. And then in the oxidation half reaction, it loses the electrons. The aluminum started off with a charge of 0, but ended up with a charge of +3, so that must mean it lost 3 electrons in the process. And now, very simple, all we have to do is the same way that we would balance a chemical equation with by the atoms, we do it with the charge as well. So we take the least common multiple of them both, so we end up with the same number of electrons traveling, and that ends up with 2 aluminums and 3 coppers. So now we have a charge of +6 over here, 3 times +2, and a charge of 6 over here, 2 times +3. And there's the same number of aluminum and the same number of copper. Oop. During these reactions, there's a lot of rules. Of course, just like the English language, there's a lot of caveats as well. But these, in general, are the rules that apply to these reactions and help you at least get started. Namely, that the oxidation number of a free element is 0, the aluminum and copper in solid state before, and then oxidation number of oxygen is usually -2. But from those 2 rules, you can usually find out what's going on. So here's the homework question that will be given to the students in the future. Similar to the last one, except where you also have to balance the number of hydrogen as well, as you can see. And so here's a chart of the electrochemical potential, and this is where you decide how powerful your battery can be. And you would think that you would want the highest difference between the 2. For example, if you use lithium and cesium over here. The only problem is that those reactions are very violent and hard to control, and so it's a balance of having the largest potential difference as possible with the safest reaction. And so the color-coded ones are the ones we're going to go into next. Iron chromium, and then bromine sulfide, and then all vanadium. Iron chromium was the first ones. We were talking about NASA earlier. They revived the redox flow battery. It makes sense. It's easy. The materials aren't terribly expensive. Chromium is a little expensive, but the biggest problem is that the chromium itself reacts very slowly, and so you have to really add a ton of voltage to push it along, and that just makes it not very useful in most applications. Also, the biggest problem with these is that if your membrane is there to separate your materials while allowing ions to cross. But a lot of the times the materials can cross through and sneak through, and that just starts to degrade your battery. And that can also create side reactions that corrode your materials and just gunk up the whole system. The next one is polysulfide bromide redox reactions. Here's the primary reactions going on there. They were originally promising because the materials were so cheap. They built a demonstration project in England in 2002, but they just had a lot of problems with the engineering and getting the flow right, and with scalability and making it a useful system. The biggest problem with this one is that some of the side reactions can create really toxic gases, and no one wants that in their backyard. And it has the same problems with species crossover and degradation, etc. The latest and greatest is the all vanadium flow batteries. This one is great because the vanadium, if it crosses over, it's not that big a deal. You just have to charge the vanadium the way that you want it for the reaction. But if there's a little bit of crossover, it's no big deal at all. It's the most common one. A lot of the startups now are using it. Vanadium mining is getting bigger and bigger because they see an option. Problem is, vanadium is very expensive. So here's a cost comparison of the iron chromium and the vanadium flow batteries. As you can see, the membrane is very expensive. It is by far the most expensive part of the iron chromium batteries, and if it degrades all the time and you keep having to replace it, that really does add up to your total O&M costs. The vanadium on the other side, the membrane is still a substantial chunk, but the problem is the vanadium itself is so expensive as a material, and material costs generally don't go down. The material is a commodity, that's just what it costs. And with it being such a huge chunk, it's going to be really hard to cut down on the total capital cost if the material doesn't get any cheaper. Here's an example. So on the left, we can see the discharge capacity of the blue is the iron chromium, and the red is the vanadium. Just like your phone, over the course of 2 years or so, it seems like it holds less of a charge. The same thing happens with these. But vanadium does tend to keep its capacity much more than the iron chromium does. And then here on the right side, we have the total cost versus your duration of discharge, which is very important for long duration energy storage for large grid applications. And again, we can see the blue is, well, they switched this time. The blue is the vanadium, and the red is the iron chromium. And as you get to the large discharge duration, that's your capacity of your battery is decided by the amount of material you'll have, and so vanadium is just going to reach a plateau, and it's not going to get any cheaper. And iron chromium is supposed to get cheaper theoretically, but it's not terribly promising at the moment. So here is the standard for energy storage is pumped hydro. Usually comes in at about $100 per kilowatt hour. And then here is a couple of the different chemistries coming out for flow batteries. And again, you can see vanadium plateauing due to the material cost. Some of these are apparently very optimistic, but it is possible theoretically for some of these flow batteries to meet the DOE, their target, and then eventually end up being cheaper than pumped hydro. But at the moment, they tend to be all around about here $200 to $250 per kilowatt hour. So some new designs coming out. There's a hybrid flow battery, which is kind of a combination of a regular lithium battery, but still having one side pump. So basically, instead of having the two tanks, you use a regular lithium anode like you do in lithium-ion batteries, but then you pump the electrolyte around it. And it's pretty promising, but right now the big problem is cycle life. It can only do maybe a dozen cycles, and it's hard to reverse the process and recharge the battery. But this is one of the more promising designs that's coming out. Additionally, there's membraneless batteries, which sounds very optimistic to me, but the whole point is that they rely on laminar flow, so they introduce the materials together and hope that they don't mix by staying in laminar flow and very stable, and then split back off. And that allows them to freely trade ions without mixing, theoretically. But there's a lot of research going into membraneless flow batteries. And then finally, there's organic flow batteries. They tend to be a lot safer. The organic materials are much more stable, cheaper, but they tend to have less of a voltage potential difference, and there is some corrosion problems when it comes to the membranes with those. So some advantages of flow batteries. It's just like a car. If you think about the power being determined by the engine size and your capacity determined by the fuel tank, and they're independent, that's the same thing with this battery. You can make it last forever with low power, or forever with high power, or you can change it however you want depending on your cell size and your tank size. It doesn't bleed. For example, if you leave your laptop not plugged in your backpack for 2 weeks, it's going to have less capacity later on, and you wonder why your battery's at 80% if you haven't even used it. Because these materials are just stored separately and don't react, that's not a problem with flow batteries. Additionally, they can recharge super fast. So let's say you're at a high intensity time of the day where you need a lot of power, you start running out of power, you can use the same cells, but instead you can just cut off your initial tanks and open up 2 new tanks, and it's like you have a brand new battery ready to go. It has the ability to deep discharge. You can go all the way to 0%, unlike lithium, which has about a 20% cap on either side in order to prevent damage. You don't have to worry about that with flow batteries. Because the electrodes aren't the reactive species, they don't degrade, which is a huge problem with the nickel cobalt in these lithium batteries. It's easy to tell the state of charge. You can just run a voltmeter inside of your sensor, inside of your material, and the voltage tells you your capacity. Disadvantages are the big ones. It's very expensive, at almost double the cost of pumped hydro, and it's going to take a renaissance moment for those costs to come down, as they're mostly related to materials. A lot of times it's more complicated because you have pumps and you have these tanks and all these seals, and the membrane is very expensive and is usually corroded. So that tends to be, and you're dealing with fluid flow, which is much more complicated than steady state reactions, which can add to your O&M costs. And the biggest one, it has low energy density. These things have got to be big. So they're never going to be powering a car or cell phone, but they're going to be, but they're great. That makes them great for grid applications where you have a ton of space out by a substation or something like that. And then finally, currently they have low efficiency, especially compared to lithium-ion batteries, 70 to 80% just within the system. But then also, once you add in the inverters and everything, it gets down to about 60%. But its applications, the biggest one is going to be load shifting and reliability, or arbitrage, where you buy low and sell high with your electricity. So here is an example of a load curve for the day in a place with high renewable penetration, in this case solar. And one of the big problems facing utilities today is that when they get down, right when the sun starts setting, is when right around like 5, 6, 7 o'clock, is right when everybody's using the most energy. That's when your solar cuts out. And so this very fast ramp up is very tricky for these utility operators to deal with. And so what you can do is buy your electricity and charge your flow battery when it's cheap with this very high solar, and then use it to shave the peak and allow you to run your base load supply of your natural gas plants and nuclear and hydro at a much more level area, or level power. Secondly, it can serve in the capacity market. All of the independent system operators and around the country have wholesale markets where you can buy and sell electricity. One of the things they can pay you for is to have capacity. So during that peak time, currently a lot of really dirty natural gas and coal plants are fired up to serve that peak that are very expensive. But what you can do throughout the day is charge it from the power grid when it's cheap overnight. You can use, if it's too windy or very sunny for a while, you charge up with the wind and with your biomass and your hydropower, etc. And you can use a large vanadium battery or large flow battery system as almost a virtual power plant, because it can react very quickly, and it tends to be cheaper and a lot less dirty than using those peaker plants. And finally, due to its very fast reaction time, the same thing goes for lithium-ion batteries and flywheels and many of the other ones, but it can provide ancillary services, which is just a way of, they call it value stacking, where they can, instead of just supplying energy, you can get paid for these kind of services as well. For example, here is an example of the load curve in red, and the green is us trying to meet it. We're never exactly on it, but we're close enough. But trying to track that requires a very quick reaction time from our power sources, and allows us to stay with the 60 hertz that we're supposed to be trying of. And then here at the end, I just have a glossary of terms that should help anybody with the homework, the basics of the batteries, etc. And then a much larger, much comprehensive voltage potential chart. That's my presentation. If you have any questions, too bad I'm not there. But go ahead and email me if you have any questions. I'm working with a lot of these with my internship this summer for Enel Green Power. And I can kind of steer you towards some more research into some of these companies if you'd like to know. Thank you very much. You have a good day.